I thought you could do your own way.
Sorry, in an authentic way.
Okay, thank you very much. So, unlike what we've just had, I'm not going to tell you about a theorem or a proof or anything, but rather about some things that we can't do. So, essentially what we've heard about Markov chain methods so far, it's almost trivial to show that it's ergodic. It's probably a bit harder, but not so bad to show that it mixes in polynomial time, and you're really after n log n or something like that. Well, here we're right at the other end, and in many cases we don't even know that the Markov chain is ergodic. So there are some challenges here, some hard challenges, I think. Right, now let me see. Works. Okay, so a Latin square. I'll start off with Latin squares. They're the first and original type of this kind of triple system that was studied. So a Latin square is just an n by n array. Each cell contains one of n symbols. Each symbol occurs once in each row and once in each column. So there's an example. This is actually an interesting example. It's a window in the dining hall at Keyes College, where I am at the moment. And it was designed by Anthony Edwards, who took the design from the cover of Fisher's book. It doesn't actually appear inside the book, but obviously somebody was sent away to make a 7 by 7 Latin square to put on the cover. They came up with this one. And Anthony Edwards asked everybody, what's special about that particular Latin square? Nobody seems to know. My suspicion is that what's special about it is that it's not actually special in any way at all. Which in a sense fits with Fisher's philosophy, because as I'm going to say a bit later on, Fisher was interested in agricultural experiments, and when you design an experiment using a Latin square, you then have to randomize before you actually lay out the experiment on the plots. And Fisher's original idea for randomizing a Latin square experiment was to work out all the possible 7 by 7 Latin squares, write them all on a piece of paper, pick a random piece of paper out of the pack and use that one. Well, more or less that. Nowadays, I think you wouldn't go to those lengths. You would just take a single Latin square and randomly permute the rows and the columns and the entries. But there may be other situations in which what Fisher had in mind is still necessary. So let's not rule this out. It would be good to be able to choose a random Latin square. But just before I go on to that, a short commercial break. If any of you are around in Britain for a little longer after the conference, there's an exhibition by the artist Raymond Brownell, who actually is a retired architect. He was one of the people who worked on the design of the Sydney Opera House. Now he's an artist, and he does pictures with some mathematical content, and very often based on Latin squares. And I won't analyze this one for you, but there are many others. He uses Latin squares in a very intelligent and artistic way, and these are not at all random Latin squares, these ones. The colours are carefully chosen, but you may like to go along to South London and take a look at the...
They are Latin squares.
Well, this one here, it's not quite so clear because there's something else overlaid onto the design, but there are others where it is just simply a Latin square or a pair of orthogonal Latin squares or something like that. He has many pictures like that. If anyone wants a card, I have a few of them here, so just ask me afterwards. Okay. Well, there's a relationship between random sampling and counting. How many Latin squares are there? Well, we don't know. The upper and lower bounds are asymptotically the same logarithmically. Number of Latin squares is about n squared log n plus O of n squared. But in terms of the actual value, that's a huge gap. So the upper and lower bounds differ by the exponential of n squared. And we don't know what the truth is. Numbers are known up to 11. there's the number of Latin squares of order 11 from Brendan McKay and Ian Wanless. But beyond that, it's not known exactly. It's even the, as I say, even the approximations are pretty rough. So, well, let's forget about that and think about, might we possibly choose at random? Why would we want to choose at random? Well, you might want to say, well, there's this huge space of Latin squares. What do they tend to look like typically? If you ask somebody to write down a Latin square of order n, they'll probably do something like this. Something cyclic like that. That's not at all typical. It has many special properties that the typical Latin square doesn't have. So how do we explore? What are the sort of typical properties? So sort of things that we might like to know. Well, let's assume, as I did there, that the symbols are the numbers 1 to n rather than pretty colours or anything like that. How many transversals? I'll define these words in a moment. How many transversals does a Latin square typically have? How many orthogonal mates? How many intercalates? As I say, the definition of those is, well, let's just skip forward to it, actually. There's a Latin square. A transversal is a set of cells, one in each row, one in each column, and one containing each symbol. So typically, how many transversals are there? And an orthogonal mate is another Latin square, which, when you superimpose it like that, each pair of symbols occurs precisely once. So if you choose a number, let's say 3, and choose a letter, let's say B, there should be exactly one cell in which 3B occurs, and there it is over on the right, and similarly for any other combination. So how many orthogonal mates does a typical Latin square have? And an intercalate is two numbers that can be just swapped over like that without destroying the Latin property. Or if you want to think about it this way, it's a 2 by 2 subsquare, 2 rows, 2 columns, 2 symbols inside the whole big Latin square. So how many of those do you typically have in a Latin square? So those are some of the things that you might want to know. Well, let's come back. Here are some other questions about typical Latin squares. You can always rearrange the columns to make the first row consist of the numbers from 1 to n, as I did over there. Well, if you do that, then the second row is a permutation of 1 up to n, and it's a derangement. It's a fixed point free permutation, because you're not allowed to have the same things under one another. It wouldn't be a Latin square. So the second row is a derangement. Are all derangements roughly equally likely for a random Latin square? They won't be exactly equally likely because, for example, if you take n equals 4, if you start off 1, 2, 3, 4, there are essentially two essentially different ways that you can continue. You could put 2, 1, 4, 3, or you could put 2, 3, 4, 1. This has just 2 continuations. This has 4. So one kind of derangement is twice as likely as the other. But that's small numbers, and there's very, very convincing evidence that as the numbers get larger, the number of completions of any 2 rows tends to be the same, independent of which 2 rows you pick. And here's another thing. Each row is a permutation of the numbers 1 up to n. Permutations are even or odd. So you might say, how do these parities behave? Are they essentially independent? In other words, is the number of odd rows behaving like a binomial n²? Or is something else happening? Well, I'll say a little bit about that later. So we've seen this. So we want a way to choose a Latin square at random, and there is a Markov chain method for doing this. It was invented by, I've said all that. a Markov chain method, so the distribution will tend to the uniform distribution if you're prepared to wait long enough. And this was Jacobson and Matthews in the mid-1990s who came up with this idea. I'll show you how the idea works in a moment. So we're going to, if I just look at what I've got here, suppose I wanted to change that 1 into a 2. So I want to perturb this Latin square slightly by changing that 1 into a 2. And I'd have to change that 2 into a 1, that 2 into a 1. This 1 would go into a 2. Everything would be fine. But if I tried to do that with this one over here, if I change the 1 into a 2, that 2 becomes a 1, that 2 becomes a 1. What do I do with that 3? I'm stuck. So they allowed things that they called improper Latin square, so that you're allowed to have one fault in your Latin square. And in this case here, essentially the fault would be, I take that and I go to 2, 1, 3, 4, 1. Now, I want to remove a 1 from that position, except there isn't a 1 there, and I want to put a 2 in. So think of what's going in there as 2 plus 3 minus 1, right? And the rest remains the same. So allowing for the fact that there's a negative entry in there, it's still true that I have each entry once in each row and column. If you look at the second row, for example, there are 2 1s and a negative 1. That makes 1. There's 1, 2, 1, 3, and 1, 4. So we extend the space to allow these slightly...
Say again, what are you putting in that space?
I'm putting in 2 positive entries and 1 negative entry. So the 2 and the 3 are both there.
In a multiset, the 2 and the 3.
It's a multiset with negative multiplicities allowed.
Oh.
Right? So the 1 has multiplicity minus 1.
Oh.
Right,
Right?
the confusion was you don't do the arithmetic.
I don't do the arithmetic. That's right. As they say in the Sudoku instructions in the Independent, no mathematics is required. Use reasoning and logic. Okay, so that's the basic step. And here it is written out formally. We have a Latin square in which the entry in row I in column j is k, and we want to change it to k dashed. So the entry k dashed already occurs in row I and in column j, as we saw over there. So those entries have to be changed to k to keep the numbers correct. And that leaves you with position I dash j dashed, where you need to remove a k and put a k dashed in, except there mightn't be a k there already, in which case you create a fault. So here's the general picture for what's going on. We start off with the thing on the left, k, k dashed, k dashed, k double dashed. So k becomes k dashed, k dash becomes k. So though column j and row I are fine, but we have to put k dashed in there once, k double dashed once, and k with multiplicity minus 1, and then again everything occurs once in that row, everything occurs once in that column. So
And after doing this many times, you can get defects. I mean, you can get strengths plus 2, plus 3. Or
No. This is what they say. Now suppose, you see, now we've made a move from a Latin square and we've got an improper Latin square. Now the rule is you've got to fix that fault at the next step. Now, when I fix that fault at the next step, you might think that that's deterministic, but it's not quite, because if you look at this fault here, I've got to remove the minus 1, so I've got to put a 1 back into that position. But there are 2 1s here that I could choose to swap it with. And there would be 2 1s in the column, and there'll also be also the 2 and the 3. So in fact, I've got 8 choices of where to move from an improper Latin square to fix that fault. Of course, it might transfer the fault somewhere else, but the idea is I will never get more than 1 fault, and the structure of that fault will only be 2 positive and 1 negative entries. So I don't get any kind of blow up in the amount of badness that occurs. I control the amount of badness. So I wander around. I've got this space with the proper Latin squares and the rather larger set of improper Latin squares. I start with a Latin square. I wander around. After a while, I come back to another Latin square. That's one step, right? Now,
How do you know that you get back to the
Well, you do with high probability you get back in a polynomial number of steps. In fact, this is in the Jacobson and Matthews paper. It's not obvious, but this is one of the things they prove. So anyway, sorry, to summarize what I've been saying, choose a random cell with entry k, change it to a random entry. There are n squared times n minus 1 moves that do that. For an improper Latin square, you have to fix the fault, and there are just 8 possible moves that you could make to do that. The random walk is reversible. If you think about it in the whole space, it's reversible and connected, and so the limiting distribution will be constant on the proper Latin squares, constant on the improper Latin squares, the ratio of the constants being the ratio of those two numbers, and that means that if I get back to the proper Latin squares, well, that's connected, and that it's the limiting distribution is uniform. So, as I just said, from any improper Latin square, you can get back to a proper Latin square on average in a polynomial number of steps. And there's also they also have a polynomial upper bound for the diameter of the graph that we're walking around. So it is connected, it is ergodic. How rapidly does it converge? Well, this has been open now for more than 10 years, and I've certainly asked many people about this. Last week, Mark came along and gave us, so to speak, permanent residents here a quick crash course on mixing and explained the coupling technique. So I thought about this over the weekend. Is there any chance of using coupling to get some estimate on the mixing time for this Markov chain? Well, how would you do it? You start off with 2 Latin squares. You want to couple them. So you make a random move in one. You make the same move in the other. In other words, you choose a position and you choose a new entry you want to put in that position, and you do the same in both the squares. But the trouble is that is very likely to create an improper Latin square, and once you've got to an improper Latin square, your moves are much more restricted, and there's no guarantee that the moves that work in one will also work in the other. So, you wander around in the fog of improper Latin squares. When you come back to a proper Latin square, you may have undone the good work that you did in that first initial step, and it seems really quite difficult to put any kind of control on what's going on there. And I'm not able to do it, but if anyone wants to think about that and come up with something, I'd be very grateful to have some ideas about that. But anyway, so the thing is at least connected, so we can at least use it and run it for a conservatively long time and hope that we get something like random Latin squares and look at them and see what happens. So here's a little bit of information. The guess about all derangements being equally likely in the second row, I've run this with Latin squares of order 20 or 30 or so, and it seems to be astonishingly accurate. I mean, it really does seem to be true, but I can't prove anything, but the evidence very, very strongly supports that. The parity of rows business is a little bit more interesting. I told this problem to Thomas Prellberg, and he wrote a program which explores into the tails of a distribution. And so here we've got this distribution of the number of the parity, the number of rows of odd parity, let's say, which is something like a binomial. Well, the agreement is mostly pretty good, but it turns out that if you look right into the tails, the probabilities are a little bit higher than they ought to be. They're exponentially small, but not quite with the right constant. And one interesting thing about that is that there's a result of Hagfist and Janssen, where they showed that the probability that all rows have the same parity is exponentially small. Now, it should be 2 to the minus n for each parity if the guess about binomial was correct. Well, they get exponentially small, but with a constant not as good as 2, so a smaller constant than 2. So I don't know quite what to make of that. This effect, to some extent, seems to be going away as the squares get larger. We've done up to size 100 for this, and there's still a slight effect. For small Latin squares, this kind of estimate is biased by the fact that, well, for example, up to order 4, every Latin square is the Cayley table of a group. And for a group, either all the rows have the same parity, or else half have even parity and half have odd. So it's nothing like binomial. And the fact that there are quite a lot of small groups and they contribute a certain amount to Latin squares is obviously going to bias the thing and put more weight into the tails than you might expect. But well, I just don't know quite what to make of that. So there's another interesting problem there, I think. But can we generalize this? There are other kinds of triple system to which you might try to do this. And the people who think about Latin squares often think about Steiner triple systems as well. A Steiner triple system, you have some points and some triples, and any 2 points lie in exactly one triple, a triple being just a 3-element subset. So something like the famous Fano plane, where there are 7 points, any 2 of them lie in a unique line of that figure. How could you describe that another way? Well, think of the set of all 3-element subsets. Each is weighted 0 or 1, and the sum of the weights of all the 3 sets containing a given pair of elements should be 1. So if you do that, now this business about allowing one fault works in the same way. You can give one triple a multiplicity minus 1, and that has to be corrected by 2 triples with multiplicity 1 through each of the pairs of points in that. So again, there's a possibility of setting up something like the Jacobson-Matthews Markov chain, and you can do that. And for one factorizations of complete graphs, that's coloring the edges of the complete graph on n vertices with n minus 1 colors. You can do that whenever n is even. There are a lot of them. Similar estimates n to the constant n squared in all these cases. So similar large spaces, we don't know exactly how large. But again, it seems that you can wander around these things. But in these cases, we can't even show the first thing that Jacobson and Matthews showed for Latin squares. We can't even show the connectedness of the Markov chain. Is it possible, for example, to get from any Steiner triple system to any other by a sequence of these moves? Up to 15, that's true, just by running the chain until you catch everything. A complete classification is known, so you can just prove it directly. But beyond that, it seems very likely that it's so, but a proof is still lacking, and similarly in the other case. So that's one kind of generalization. And of course, even if you could solve it, you'd still have the problem of trying to say anything at all about the mixing time, which is probably even harder for these than it is for the Latin squares. But there's an even more general setup in which you can frame all of this, which I'd just like to say something briefly about. Essentially, if you think about Latin squares described as I described them, any pair of a row or column or row or symbol or column or symbol must occur exactly once. Now you can replace 1 by a fixed positive number lambda. And in the case of the Steiner triple systems, you could say let any 2 points be contained not in just one triple, but in lambda triples. So you get a block design with any 2 points in lambda blocks. So balanced incomplete block design. And there's a generalization of the one factorizations as well along similar lines. And the general idea works the same. Let me just take you quickly through the definition of this kind of design. They can all be done in a uniform way. So we're looking at triples. So you take the number 3 and you take a composition of it. 1, 1, 1, 2, 1, or 3. 1, 1, 1 will correspond to the Latin squares, 3 to the Steiner triple systems, and 2, 1 to the one factorizations. So we choose sets x1 to xm, one for each part of the composition. We choose a block to consist of k1 points of x1, k2 points of x2, km points of xm. So for example, in the Latin square case, x1 is the set of rows, x2 is the set of columns, x3 is the set of symbols. Each entry of the Latin square picks out one row, one column, one symbol. In the Steiner triple systems, it's just one set, and a block is a set of 3 elements from that block. So anyway, the property that we need is that if you choose, if you take some numbers t1, t2 up to tm, adding up to 2, well, this is rather trivial, but this is what it would say. You choose subsets of the xi's of the appropriate sizes. There should be a unique choice of the k's containing the t's. So just to go to the Latin square case, if I choose 1 point in x1, 1 in x2, and none in x3, I've chosen 2 points subject to these conditions. There should be one triple containing both of them. Don't worry too much about that, but just have a look at where it says here a unique, because we're going to generalize that by saying a constant number lambda in a moment. And the same, so for Latin squares, we have 3 sets, rows, columns, and symbols, and each triple picks out a row, a column, and a symbol. That's one entry in the Latin square. The case where the composition is just 3, we have a single set, collection of 3 element subsets, only 2 points lying in a unique one. That's a Steiner triple system. And the case 2, 1, we have 2 sets. You think of them as a set of vertices of the graph and the set of 1 factors, or colors that you're putting on the edges, if you like. And a triple consists of 2 vertices and the color of the edge joining those 2 vertices. And again, you pick 2 vertices, they have a unique color. You pick a vertex and a color, there's a unique edge of that color passing through that vertex. So all the conditions are satisfied. That's a 1 factorization. So in those cases, the ones where we have this Markov chain working, and we can allow a fault, one object can have multiplicity -1. Everything works as before, except that we can't prove the connectedness. I've tested it for Steiner triple systems, not for 1 factorizations yet. No proof of connectedness. And we can replace the word a unique by a constant number lambda. So we're having in one case 2 designs, or balanced incomplete block designs with block size 3. In another case, these are things called orthogonal arrays. In the third case, it's a little bit more forced, but you take the complete graph with each edge repeated lambda times, and you want a lambda factorization. So you want to factorize it into lambda regular subgraphs. And you can walk around those, except that, of course, we don't know whether it's connected. But hopefully it is, and in which case we have Markov chains for all of those things. We know nothing about how long you have to run them to get close to uniform. Further generalizations could be imagined and might be useful for some purposes. But so what can't we do? Well, there are quite a lot of challenging problems which I don't know how to choose uniformly at random. Choose a random Latin square orthogonal to a given Latin square, for example. Or a random pair of orthogonal Latin squares to make it slightly easier, because in the first case there are some Latin squares that have no orthogonal mate. Well, I wouldn't be much point trying to choose those. But can we choose at random a pair of orthogonal Latin squares? A random filled Sudoku grid. Well, for 9 by 9 Sudoku, you can do it by what I might call the Fisher method. You can just make a list of all of them. That's been done, actually, and pull one out. But for n squared by n squared, how do you do it? How do you choose at random from that? Balanced incomplete block designs with block size larger than 3. How do you choose randomly from those? These are all things where the search space is huge, and you might like to try and get your hands on it by some kind of Markov chain method, but as yet we don't know how to do it. So, thank you. Yeah.
There's a natural walk on Latin squares where you just pick a square and a new number, and you make that change, and that causes you a problem in the row and a problem in the column. So you go to like column problem and change that, and that gives you. So you walk around, and eventually you'll close up.
So you just take a pair of rows, do you, essentially?
No, just start with a position and choose to change the number, and that'll give you a clash in the column, and so you then go and you change that to resolve that clash, and then I'll give you. So you walk around.
You walk around between rows and columns.
Yes.
Yes.
You walk around, and eventually you close up, and that's what moves.
That's not uniform, I believe. Depends on the number of intercalates, for example. If you have an intercalate, then this closes up very quickly. But for for squares with no intercalates, you might have to wander around a long time before you get back. And I think this makes it non-uniform.
But I mean, do we know things like whether the set of Latin squares is connected under these moves?
I have a feeling the answer is no, but I might need a few minutes to think about that.
No, they're not connected, or
They're not. They're not.
know?
I have a feeling that they're not connected. That there's some reason why they're not connected. There is.
Is
Yeah.
there a parity problem?
There is a parity problem, but I think there's another problem as well. I think you can get stuck. Let me think about that. Yeah.
It's possible that at least the smallest of those problems could be overcome using Metropolis algorithm, right? I mean, but I don't know whether you can compute the right
Well, yes, that's an interesting point.
ratio of probability.
I haven't thought very much about that. It's certainly possible that you might do something along those
I
lines.
had another question too, which is, is it possible to say what it is about the proof of connectedness for Latin squares that doesn't carry through to these problems?
Yes, exactly. Latin squares you can build row by row. And so that's what they do. If they're trying to get one Latin square, move it to another one, they make the first row agreed and the second row, and they work their way down. And they can always localize the changes to happen below where they've got to so far. Seems to me there's some hope that for one factorizations you could do that, a one factor at a time essentially. But for Stein and triple systems, there's no hope.
Maybe this is the same as what Jim was alluding to. What if you generalize Latin squares to allow an arbitrary number of defects with a weight W for each defect, and then, so this is something like working at finite temperature rather than zero temperature.
Yes.
And
yeah,
then probably it's easy to find an algorithm, I mean, that it's connected. And then the problem is, how badly does the mixing time deteriorate as W goes to zero?
Yes.
Can you choose a W which is large enough so there's reasonably fast mixing, and small enough so that there's a reasonably big probability that you get a defect-free Latin square?
Well, that would be a good approach.
Because all of this reminds me of Jeremy Sinclair's version of getting an Eulerian spanning subgraph of a given graph, where they allow defects and put a fugacity for that. Or in the physics literature, it's basically the same thing called the worm algorithm, where you allow simply one pair of defects.
Yeah, well, it may well be. I'd be very happy if somebody would have a go at that.
Okay, well, lots of questions there. I think maybe we should break for tea now, and I think we resume at 3:40. Thanks, people.